now to why we're here to. Excellent. Thank you, Nishant. Um, got it. All right. So now to the meat and potatoes for today. We were able to reach out to and find a wonderful presenter for us today to talk about not only how do vertical axis turbines work, but also how can they be employed. I mean, there's both sides of the conversation. So we're really looking forward to our presenter today, Kevin Wolf, the founder and CEO of Wind Harvest International. So just a brief nugget about him. With 40 years of experience, he is a graduate of UC Davis, which we're very excited about, which is here in our neighborhood. Not only expert on the technologies, but also on the physics of how. So we're really looking forward to hearing more about this. So Kevin, with no further ado, I will turn it over to you.
Great. Well, thank you for the opportunity to be here. I am looking forward to this discussion. I can just jump right in, but let me give you a little bit of a background. I actually got my degree in evolution and ecology, and I've learned that being a scientist is a very useful skill and background to have when working with engineers. And I work with a lot of engineers, and I think that common science and understanding of science is a very beneficial from my background. So that's what one of the things I bring to the table. I think I'll just start by sharing my screen and going to the slideshow and opening this up so it is the full show, and I move that out of the way and view and enter full screen. Okay, that should do it. View. Okay, so we call this the going where no turbine has gone before, because the problem with the industry and with vertical axis turbines, or turbines in general, is that the traditional turbines cannot handle turbulent wind. I had looked up the wind energy engineering book 101 from UC Davis, and in it says that horizontal axis turbines are raised high above the ground and placed far apart from each other to avoid turbulence. And you can imagine why this is so. Those long blades connect to a horizontal drive shaft. If that blade drops into turbulence, it's going to shake, and it's going to then shake that drive shaft. And that drive shaft is 60 to 80 meters above the ground, and that's a difficult thing to fix. And this is an interesting picture of horizontal axis turbines and the wake they create for each other. Now, this is in early years, and they realized they should not place rows of horizontal axis turbines directly behind each other. They should stagger them because of the turbulence and the reduction in wind speed that is caused by the upwind turbines. But it gives you a sense of how much turbulence the turbines produce themselves. So that leaves this space that's near the ground and in between the horizontal axis turbines available for a different kind of technology, a technology that can handle turbulence. And that is these vertical axis turbines. Now, this is ours. We think we'll be the first company that will bring a utility scale turbine to the market. As you can see, this turbine isn't very tall. It's 22 meters. All this is in meters. To the top of the turbine, we can probably get up to maybe 30 meters tall. But you don't want to have the turbines be too tall, or they're going to create a problem for the horizontal turbines under which they're installed, right? They're going to create their own wake, and I'll show you that a little later. These turbines at our side, our turbines are 13 meters wide. The rotor is 13 meters wide by 13 meters tall. And so it's a square. And it can be put on a different height towers to reach above the ground. And this one, we're on a 12-meter tower, and the blade's 9 meters above the ground. And over here on the left, I don't think you can see it very well, but all the items in yellow, the arm fairings, the blade itself, the blade arm connections, the mast, those are all patents that we have pending for this new turbine. And the turbine is had to be made very durable to withstand the turbulence near the ground. The key things that vertical axis turbines have that horizontal axis turbines don't have is that the blade is connected at 2 points to the mast. As you can see, the arms connect to the center mast at 2 points to the blade. And that is a lot sturdier than the horizontals that have only a single point connection to their drive shaft. They align vertically, and as they go around and spin vertically, they have different loads, pushing and pulling loads on it. They have a stall on it, and 3 blades allows for that distribution of loads that come as turbulent wind bounces all over it, speeds up, gusts around it, that it distributes it, and it reduces the amount of wear and tear that you would see in a horizontal axis turbine in a turbulent condition. And then the last thing is the inventions we have that provide for the ability to withstand this kind of turbulence. And I'll go into that next. Let's see what's going on here. Okay. So the first thing I'm going to talk about is this blade arm connection. And that is the area that is weakest on a vertical axis turbine. There is a Darius, a egg beater type turbine called the Flow Wind. In California, they put in 500 of these in the 1980s. And those 500 turbines started to wear out at about 5 years in, where the arm connected to the blade. These turbines rotate 15 million times a year at the RPM that they're operating. So at 15 million times, anything that has a push and a pull with every revolution is going to have a lot of stress on welds, on bolted pieces, so you got to deal with this stress. And so here is the our blade arm connection. We have a little transition fairing made out of fiberglass that connects the blade and reduces the amount of drag that's there. And this is our invention. It is a hinge mechanism between the blade and the arm. And as you can imagine, a hinge with a pin, and a very hardened pin, a pin that can handle those stresses, that's where the stress is. It's on that pin. And it can handle the movements, the minor movements that are going to occur 15 million times a year, twice each rotation. And it's all in that pin. And then when you need to replace that pin, well, that's much easier than replacing an arm connection or a blade or the other way. So pins are very good ways of handling a lot of motion. The other one I want to show you is the end of the blade up here at the top. And I'm worried that this stuff is going to be in my, well, I'll show you. So this blade is, it is an extruded aluminum blade, 6061 T6 aircraft aluminum alloy. It is the largest blade that can be extruded in the outside of Russia and China. It's made by Step G out of Germany. And what the invention is that we figured out how to change the interior of the blade so that it can remove the need for a plate that was previously epoxied on the outside of the earlier versions of the blade to help withstand the loads that are connected between that arm and the blade. The other interesting part of this is sliding this nut bar down those tracks to line up where the connector piece, I'll go back a piece on this, there, lines up. You have a nut bar inside there. It's quite easy to bolt it in if the nut bar is in the right location. And I'll show you a slide in a bit where the old version was, and you can see, well, yeah, this is quite a big improvement. And this track inside adds to the strength of the blade and removes the need for having to have a plate on the outside. And we have a patent pending for this as well. And now this is where the last kind of, it's hard to see this, but the nut bar is on the inside on the right, and on the outside, it kind of shows where it lines up, and you bolt that hinge mechanism to the plate. and you can see how the stresses are spread out over the blade more, and the pin is holding the stresses. The other interesting one we have, and I'm going to try to move this down here so it's out of the picture, is the arm mast connection. Now, over here on the left is the old version, model 3.1. Almost all vertical axis turbines have a pipe for a central mast. And I'll show you some pictures of why that's problematic. One is you have to have flanges to connect pieces of the pipe together. To get just a single long pipe that's, say, 13 meters long and have it straight enough is not an easy thing to do. So we break the pipe into pieces, and then you put a flange on it, and you put a full penetration weld on that flange, and then you bolt a piece of material in between each section, and there's where the arms connect to a central pipe. Well, we got some with one of our team members. He had a patent for a nut bar that would slide into a long tube, and that nut bar allowed us to rethink the entire mast. And we came up with what on the left is a $24,000 mast in a single order to a $6,000 mast on the right-hand side, because it's easy to bend metal into very straight pieces of metal. And now you have flat sides, and flat sides allow for bolting right onto the metal. Now, the trick on this is, how do you get some kind of nut bar? You can't put a wrench way down in there and try to hold a bolt on it, then bolt it from the outside. You have to be able to slip in a nut bar into the inside, pretty deep inside now, meters deep, into this mast to bolt on all those plates. And that is the invention that we licensed from North Star Wind to make this come together like this. So now we have pretty much all bolts and plates. Very simple, easy to make plates, very simple and easy to bolt them together. And you can see the arm mechanism connects to the mast in another hinge. We couldn't quite get the extreme loads in the certification process met until the team came up with, let's add another hinge here. And once that hinge was added, we could meet all the load requirements. And that hinge also can handle this kind of minor movement 15 million times a year. In a hinge, it's much better to do it there than in a bolted straight to the mast. So those are some of the examples of the patents that we have pending that give us the ability to withstand these kind of very turbulent forces near the ground. And to give you an example of turbulence, the Model 3.1 turbine had a experienced 10-mile-per-hour gusts in 1 second. And within 1 second, the wind speeds changed 10 miles an hour. Now, one of the great things that we had was the California Energy Commission required that we go through, we tell them what technology readiness level we were. And I had not heard of technology readiness levels, and this was a few years ago, and it was a very helpful process to go through. Now, they didn't have technology readiness levels strictly for wind turbines, but they had them for airplanes, spaceships, all kinds of stuff. They're very much spreading now. And the Energy Commission and the Department of Energy, NREL, require that you declare what technology readiness level your product is at before you can apply for a grant. So going through the different ways of looking at it, we determined that technology readiness level 6 would be a full-scale prototype. And we accomplished that, and I'll just go through the last ones, and I'll show you in the next slide our sample examples of them. The next one, which is technology readiness levels, would be a full-scale prototype in industry conditions. In our case, very turbulent wind. 8 is third-party certification. So some third-party body, in our case, the U.S. Small Wind Certification Council, will be using IEC 61400-2 standards, will certify our turbines. Technology readiness level 9 is banks will finance your customer loans for projects, multi-million-dollar loans. So what does a bank need to be able to do that? Talking to due diligence officers for wind companies, they want to see that you've got technology readiness level 8, and they want to see that you have 10, 50 turbines operating for a year, 2 years, and they want to see the data. They want to see the repair time, the operational uptime, the efficiency. They want to see your computer models, and then they will loan money to your customers. So that's the end of the technology process. Now here, I'm going to move that up here so it's out of the way, is our turbines going through the process. So technology readiness level 5 was our first 3-bladed turbine. And it is a 25 kilowatt turbine. And if you look closely, you'll see that it has guy wires. All of our previous turbines always had either stators or a guy wire to hold the center mast. And a large part because we could not predict harmonic resonance. And so we had a single speed. We figured out where that harmonic resonance occurred, and we set the single speed to operate outside of where the harmonic resonance would occur. It reduced efficiency. It wasn't a variable speed drive. You couldn't keep the tip speed ratio optimized, but it was a way to get around this problem of not being able to predict where harmonic resonance occurs. Guy wires and have their own problems. They're not easy to do on sloped land. They really work better in flat land. And if you're going to do all over the place, well, you're going to deal with slopey, hilly land, and they're going to need a turbine that's cantilevered. So this is where our cantilevered turbine comes in. A team of engineers, young engineers, figured out how to do this and built it, but did not have an aeroelastic model and could not predict where the harmonic resonance would show up. And it showed up right in the middle of the operating range. At 42 RPM is where we found the harmonic resonance. And it had difficulties there. And I'll tell you a little bit more about that story later. But essentially, we brought in Dr. David Malcolm, who brought in an aeroelastic model that was developed initially out of Sandia National Labs. And we used the data from this full-scale prototype to validate the model and to confirm its accuracy and harmonic resonance. And then we made model 3.1. And 3.1 is operating down in Texas. It is a full-scale prototype. It's got a number of different problems on it, but we learned a great deal from it, and it led us to the model 4.0, which we have ready to go through technology readiness level 8. So I'm going to go to this next slide. There is two of our key team members. Dr. Malcolm we grabbed him out of retirement. He is the expert in the aeroelastic modeling, and he's got 40 years of experience in horizontal and vertical axis turbines. And Dr. Ala Jala, she is our principal engineer, joined us a number of years ago, and she has learned everything she can from Dr. Malcolm on aeroelastic modeling. And we're very happy to have the two of them on our team. This is a Campbell diagram that kind of shows the harmonic resonance and the frequency response of the technology. And in this case, you can see this little circle. We experience in model 4.0 at a technology readiness level at 26 RPM. And that's a crossing between the 2P crossing, which is the blades, and the overall turbine. And that is when these harmonic resonance cross each other is where you get the most resonance and the most problem. So we motor up to 30 RPM, and then we operate between 30 RPM and 55 RPM. So we just speed up through that 26 RPM, and we bypass the harmonic resonance. We kind of jump over it. And then we don't have any other harmonic resonance during the operation of the turbine. And now this is there's a great report. I'll be glad to send it to you. I put my email in the chat, and David Malcolm wrote up a great report that evaluates Model 3.1's data against the aeroelastic modeling. And this is an example of one of the things he looked at is how accurate is the bending of the 1P ratio. And it comes out to be quite an accurate estimate of what the model predicted versus what the data showed. And it was one of the fun things about this tech process was realizing, yeah, the modeling is very good. So this is an interesting part of the process. As it moves around 360 degrees, that's the x-axis on the bottom. And you can see that there's a prediction of what kind of blade bending loads there's going to be across the blade. And how accurate does the data follow the model? And it's a little bit off, but it pretty much follows quite accurately. And the big one is this downwind shadow. So you saw, I think earlier, that the tower, it intrudes into the rotor. Well, there's going to be a bit of a shadow effect behind there where the power is going to drop. And that shadow is captured quite well in the modeling data. The model predicted it, and there it is in the data. So it was quite fun to see this level of detail pop out of the data and accurately predict with the what the model predicted. And this is another one that I like showing because one of the things that the data shows is that the fatigue life is going to be the Sandia National Lab has a frequency response model that is also creates into the fatigue life model, the life model. And the life code shows that the shortest lived component on our turbine will be the blades, and they'll last 74 years. It's an interesting problem to have of a turbine that every 20 years you refurbish it. You replace the pins, you replace the power converter, you take out the bearings off the drive shaft, replace them, you take the bearings off the generator, and maybe you rewind the generator, and you then the rest of it, the galvanized steel mast and the arms and the fairings and the 6061 T6 aluminum blades, they just keep going. And then another 20 years out, you redo it again. And your concrete pad, it lasts as long. And so now you have this very long-lived renewable energy device that's kind of like a dam, a hydroelectric dam that lasts a very long time. The industry doesn't quite know what to do with long-lived renewable technologies. They're used to having them be replaced every 20 years or so. So it is one of the benefits we have, but it is also one that is not easily monetized. These turbines here are the largest turbine that we had made before we created the cantilevered turbine. This is an early version of which the inventor, the guy down there standing at the bottom, and I'll show you another picture of him before. The concept is you needed to have this turbine, the center mast, be held straight and rigid at the top of the mast. So he has these outside stators on the points of a star, and those stators help send wind from multiple directions into the center of the rotor. And what he noticed when he did this is that one of the stators was being beaten up in the corner. And he realized that the wind was speeding up between the stator and the blade. And that was creating more friction and more wear on the stator. And he then hypothesized that, if I put two turbines close together, I will get the same benefit of the increased wind speed that the stator creates without having to spend all that money on the concrete foundation and the stator itself and everything else. So that's Bob Thomas. He managed the California Wind Energy Program in the early 1980s. He's considered in some books to be the father of wind in the country, because without him, maybe we wouldn't have brought all those turbines into California at that time. He operated that center turbine for a year all by itself, collected the data. And then I was one of my first things I did with the company is I helped raise the money, and I helped put in the two turbines on either side. And the center turbine did not change at all. But what he got is an increased energy output of that center turbine by the two turbines being placed about 3 feet apart from that center rotor. And it's Bernoulli's continuity principle is the primary thing that drives the increase in wind speed. The energy output in the low wind speeds doubled for the center turbine. And the reason is each turbine has a blockage effect. It runs into the blades and it spills around. And it spills not into empty space, it spills into the neighbor's rotor. So it increases the wind into the neighbor's rotor and it goes right into the gap. And in that gap, it speeds up, according to the modeling, almost 2 times the wind speed. And then behind it, here on the right, you'll see what the vortices look like. They are shed vortices. The gap in the upper one is nice and smooth between the gap. And those blades are going with the wind. And I mean, they're going into the wind and it's nice and smooth. But when the blades go with the wind, they shed off these shed vortices. The blade tip speeds are between 40 and 80 miles an hour, which is faster than the wind. So these shed vortices behind the blades, they create a low pressure zone. And in that low pressure zone, now you have a pressure difference between upwind and downwind of the turbine. And that also increases the wind speed through the pairs of turbines. So that is the coupled vortex effect. Is when you place these turbines close together, you can get a significant increase in the energy output. And the California Energy Commission did a grant for $50,000 in 2011-12 and modeled it with one of the best aerodynamic modeling companies in the world and showed that it could work for low solidity and that it was a significant increase, and it would increase the CP max, the maximum power that a turbine can produce, to close to the levels that the horizontal axis turbines could achieve, around 45 to 50%. Now, this next one is John DeBerry, Dr. DeBerry out of Caltech, had figured out from watching fish in schools of fish that they swam such that their fins created coupled vortices. And those coupled vortices made it very easy for them to swim, much more efficient. And he hypothesized that you could do something with this for wind turbines. And he found out that we had patented the coupled vortex effect. And he looked at our turbines and visited Bob and decided that our turbines were too big for the kind of experiments he wanted to do. So he, out in near Caltech, out in the Antelope Valley, he placed up a project where he put in pairs of smaller 2 kilowatt Windspire vertical axis turbines. And he measured with all kinds of sonic anemometers and all kinds of stuff. He pulled out a lot of data and determined that what happens when you place turbines close together and you counter rotate them, vertical axis turbines, they also draw faster moving wind from higher above the ground towards the ground. And that led to a whole lot of papers from Stanford and Oxford and a big deal for the next decade as they looked at, well, what would happen if you had vertical axis wind turbines under horizontal axis turbines? And basically, it looks like you would increase the output of the horizontal axis turbines by about 10%. Now, the energy in the wind is the cube of the wind speed. So it doesn't take much of an increase in wind speed to get an increase in the energy output. So vertical axis turbines, rows of them or pairs of them, arrays of them, under and around the horizontal axis turbines will draw down faster moving wind from higher altitude towards the ground. And the beneficiary of those will be the verticals on the ground, but also the horizontal axis turbines above them. So I'll tell you a little bit more about this, how vertical axis turbines can increase the lifespan of horizontal axis turbines in a bit. The trick is you got to figure out where the wake of these turbines are with field experiments. So the way to do that is with a Doppler LiDAR that measures turbulence and wind speeds every 5 meters. And you place it downwind 300 meters or so, and you point it upwind. You get some sonic anemometers in there to validate the data, and you sweep it back and forth, and you collect a ton of data. And is it true that the shed vortices from the vertical turbines dissipate at 5 times the rotor height. So our rotor height at 13 meters means somewhere around 65 to 70 meters downwind. The LiDAR should show that there's no more turbulence from the vortices. And it should show that the wind speed is returned back to VW, the incoming wind speed from the upwind, and that you look at that upwind sonic towers and you measure that and you say, yep, if you got it, VW is returned back, then it matches what the modeling shows. But we're going to need to show this to the wind farm owners that yes, these shed vortices from the vertical turbines do not rise up, do not spread in and harm their horizontal axis turbines, because then they won't let the verticals underneath them if they harm their existing turbines. So this market for these vertical axis turbines is large. We used UL's Wind Navigator, probably one of the very best programs for predicting wind speeds around the world. An expensive license, but we got the database of 32,000 wind farms from the Wind Power Net, and we had interns use the UL Wind Navigator license to measure wind speeds for every wind farm we could find, and we found 10,000 wind farms. And of those 10,000, 20% of them had wind speeds better than 6.5 meters per second at 15 and 20 meters above the ground. And about 5% of those wind farms had wind speeds above 8 meters per second at 20 meters above the ground. And 8 meters per second wind speed is a really great wind speed. So that estimate is that you could put in a large amount of turbines over the decades to come. And if that prediction of what the past is holds in the future, we should see the amount of the wind farms with great near ground wind speeds double. And that seems to be the easiest place to build wind farms, is in an existing wind farm that has proven wind speeds, got the roads already installed, and that is the biggest market for these turbines. For wind farms that can't bring in new transmission lines, we predict that it'll be hydrogen gas development that will be done on these wind farms, because you need a very inexpensive renewable energy resource for green hydrogen. And the least expensive resource is really going to be high wind speed resources, because of that cube law. The cube of the wind speed energy is the cube of the wind speed. I'll do one last thing here. It's what's called a capacity factor enhancement project. This example is a 100 megawatt wind farm, and you add in 25 megawatts of our turbines. So now you've got 125 megawatts of combined capacity, but you haven't changed out the substation or the transmission line. It remains 100 megawatts. So up in, in the low wind speeds, you're just producing 25% more energy. And as the wind speeds get to rated capacity, rated meaning when the full energy output of the horizontal turbine is producing, you start to have to taper off some of the turbines. Now, what happens with some more of the modern wind farm projects, they'll put in 110 megawatts of horizontals for a 100 megawatt substation, so that as they get to rated capacity, they can pitch their blades earlier. If you do not have your blade pitched on a horizontal axis turbine and a gust hits it before it's pitched, the loads on that unpitched blades can be very severe, and it's one of the leading causes of damage to horizontal axis turbines is gusts hitting their blade before they're pitched. But if you have additional capacity in the wind farm, then you can pitch your blades earlier and avoid the gusts that start to come in the higher wind speeds. Then you can take the turbines that are the most problematic in the wind farm, and you'll know there are almost always going to be some turbines that are more problematic than others in a wind farm. You shut them off in the high wind speeds, and you keep the verticals going, and therefore you keep the capacity of the wind farm at the 100 megawatts the entire time. But it looks like you can extend the life of your horizontal axis turbines by 10 years by adding an additional capacity to your wind farm. Well, you can't add additional capacity to an existing wind farm. You can only add it to a new wind farm where you plan it in. because you can't add more horizontal axis turbines to a new wind farm because they're going to cause turbulence problems for their neighbors. They've already maximized the amount of horizontals they can put on a wind farm. So really the only way you can add a capacity factor enhancement project is to add vertical axis turbines underneath the tall turbines. So that is what we're raising money for now is to bring us through technology readiness level 8. We've figured out that because there's been so many disastrous wind turbine projects and fuel cells and solar and all kinds of things that the venture capitalists in the United States and the companies are not investing in new renewable technology until it's completed technology readiness level 8. So we spent the last year trying to find investors to bring us through technology readiness level 8, and we have struck out. So we're going back to crowdfunding to do that. Then we are doing a major round after that, and that puts the money into projects that gets us through technology readiness level 9, right? We need 50 turbines operating for a year or two, and no one will finance those turbines until they can get a bank loan, and the banks won't lend it to you until they've seen that many operational hours for your turbines. So that's where we are in crowdfunding and raising capital. And with that, I will stop and answer questions.
Wow, that's pretty exciting. I did have a question that here at the end. So it sounds like you're still a little ways off from having a marketable product that's available for installation in the industry. If you were able to meet those funding goals, what do you think? How long do you think it would take until you have something that's marketable for the industry to be installing?
So everything's ready for Model 4.0. We've had it ready for 6 months. We just can't raise the money.
Mm-hmm.
So the longest lead time part is the permanent magnet generator from Soga out of Italy. And that takes 6 months to make it and deliver it. But everything else is much shorter. The drive shaft is made by Scott Forge and TechMax out of Illinois. The Step G out of Germany can make the blades in about 3 months. So there's all these component parts are made by different suppliers. One of the benefits of a simple turbine like this is that there are multiple suppliers for each of the component parts. So you don't have to rely on you don't have to make your own factories, and you can rely on multiple suppliers for it. So it's 6 months out when the money comes in before that Soga generator arrives, and we can install the 2 turbines at the UL testing facility in Texas, right next to the Model 3.1 that's operating there.
Nice. Excellent.
It appears the vertical axis turbines can increase the output of the horizontal turbines. So is it just that it increases it, or it actually gives the ability for the horizontal turbines to produce more power per day over like a longer time horizon each day?
Well, that's a good question. So what you basically have is a percentage increase in the wind speed that reaches the horizontal axis rotor because of the verticals underneath it. And those shed vortices have a low pressure zone in the middle, and they draw down the faster moving wind to the ground. So you can get a 3 to 5%, 10% increase in energy wind speeds. And it could start it earlier. But our turbines don't start they're not a very low wind speed. So it's really not going to benefit at the lowest wind speeds. It's really going to just, over the course of all the way up to rated power, it's going to see the horizontals are going to receive more wind speed and produce more energy. Let me think one more thing, because I forgot about it. The horizontals end up blocking wind and send more energy into the verticals as well. So if you place these verticals underneath, there's a blockage by the horizontals, and that blockage speeds up the wind underneath the horizontals, and the verticals underneath will receive a higher wind speed. So there's a double synergy there that goes on with these turbines in a wind farm.
So do you have like a simple number of, if you were to put in the ideal number of vertical turbines on a particular location, is there a rough percentage increase of maximum power, and is there a rough percentage increase of total power delivered over a day or a year time frame?
Okay, so maximum power is going to be set by the capacity of the generator, and they will not. No turbine is going to exceed the amount of the generator's capacity. They'll pitch the blade earlier, so you can't get more maximum power, but you do get an average. The modeling out of Stanford and
So
Oxford say that
the
you'll get.
verticals don't add to that because the verticals are running at a higher rate than the horizontals. Is that it?
The verticals just bring the faster moving wind into the horizontals, and the modeling says the horizontals should get a 10% increase in their annual energy production with a field of verticals underneath.
So the verticals don't produce any power on their own?
Of course they do. That's a completely separate thing. The verticals produce their energy, but they're also going to increase the energy output of the horizontals.
Sorry. So per square mile or per square foot, whatever the density is, you'll get a higher maximum output per square foot with the verticals under the horizontals.
Correct.
And you'll get more hours of produced power because of the combination synergy between the two turbines.
Yes, we can up to triple the amount of energy output per acre of land with the verticals.
Okay.
And the verticals are going to be they're not going to be as efficient. They're going to come in at about a 45% efficiency and not a 50% efficiency. So they're not going to make use of the wind speeds, and there are going to be slightly lower wind speeds near the ground. So they're not going to be as productive as the horizontals, but they make up for it in the fact that it's much lower cost to build out the understory of an existing wind farm than it is to build a new wind farm.
And that wind farm can now operate at higher wind speeds.
No, it operates at the wind speeds it operates at. It just gets more wind coming into the wind farm.
Right, but the wind farm would shut down at a higher wind speed in the past. Now the verticals can take that higher wind speed and still operate, right?
No, the verticals and the horizontals shut down about the same wind speeds, around 60 miles per hour.
Okay, I get it. All right, thank you. I'm just going to pass it on to Peter there.
Yeah, I see that, Peter, you've got your hand up. So you want to go ahead and unmute yourself and ask your question?
Sure. Can you hear me okay?
Yes, we can.
Okay. Yeah, so it's actually not so much a question as a comment. So Kevin, I think what you've described is actually pretty brilliant. But there is one caution that I want to throw out to you is because basically interconnection to the grid is what I do all the time. And when you add more wind turbines, even if you don't increase the capacity of the plant, you add more wind turbines, you're actually going to increase your short circuit duty at the POI. And that potentially could create a problem on the grid. So, you're going to have to, if you co-locate your turbines with another project, that project, you're both going to have to work together and provide what's called a material modification assessment request to the utility, and they're going to have to evaluate it, make sure you don't create any new problems. If you don't create any new problems, then this is great. But I guess what I'm saying is, not all sites are going to be created equal. So some could be problems and some might be okay.
Oh yes, and so one of the recommendations we have, we produce reports on San Gorgonio, Solano, and Tehachapi passes, and showing the wind navigator data on how much you could increase with vertical axis turbines. And we're about to produce a whole statewide report on all the wind resource areas. And our recommendation in there is, one, validate that the wind navigator data is correct. And then two, evaluate how can you do these capacity factor enhancement projects, because they're complicated. But they could be the lowest hanging fruit in the state of California, because they may not need transmission lines, but somebody should be investing in the complicated question that you just raised there to see, well, how can you make use of these great resources and increase the capacity of the transmission lines and the substations in the land? But that's a very good point you made.
Yeah, and there are ways, they're not free, but there are ways to short circuit duty if it's a problem, but it's just, I just wanted to throw it out there as a caution. When you get to the point where you actually want to do something like this, you need to hire a consultant to help you figure that part of the film out, but yeah, it can be doable. It's just a warning. That's all.
Oh, and I appreciate it, but it's
All right.
there's a lot that's going to have to be done to do that.
Yeah, and but I just wanted to say, this is a brilliant idea, and reusing sites that are already being used for energy.
Yes, it's been the motivating the company from the beginning.
And this is one of the reasons why I love this organization, because you do get everybody from all different aspects that are looking at the problem from all the different facets. How exciting. All right, Guy, it looks like you've got your hand up. Go ahead. You can unmute
Thank you,
yourself.
Heather.
Yeah.
And Kevin, this question comes from a slightly different perspective, and just curious on this. You mentioned earlier that the speed on these turbines would be closer to 40 to 60 miles per hour on average. Was I getting that right?
The blade tip speed to be between 40 and 80 miles per hour.
80 up to 80 miles per hour. Is there any have you had any thought or study into what types of environmental compliance might occur? Because you're in the understory, closer to the ground, where there's going to be more wildlife activity. Those turbines are moving at a very high rate of speed. Is that anything at all that's come into the
you absolutely, Guy. Yes, you that is a concern. So the horizontal axis turbine tip speeds are between 150 and 200 miles an hour. And you can just do your math and say it's 50 meters radius or 65 meters radius, and then go out there and count how many seconds it takes to do the entire revolution. And you're going, wow, 150 plus miles an hour is that tip speed. And those horizontal axis turbines are two-dimensional. And wildlife did not evolve to see a two-dimensional object, especially when coming out of the sky at over 100 miles an hour, where you're not looking up and you're not looking down. And birds like hawks and eagles, they have their eyesight trained on the last 10 meters of the ground as they're chasing some rabbit or something. And they don't see this blade coming out of the sky from a two-dimensional object. So the ornithologists think that these are three-dimensional, and wildlife evolved to see three-dimensional objects. Now, you get more technical on it, the physiologists of birds say, but they have these flicker factors. How fast are their brain and eyesight seeing images, and are they remembering the image? So our blade is passing a given spot every third of a second, but do they see the space in between the third of a second? And do they remember that a blade had passed there a third of a second before? Unknown, right?
Yeah.
So we don't.
I'm not trying to dive too deeply into it. And I was also thinking kind of about because we're in the understory, the relation even to bats and their activity, which tends to be pretty close to the ground, right? I don't know that they. Anyway, I don't want to dive too deeply into it, but it's fascinating technique. Very interesting.
I want to do two more things on this thing. One, the only known study on vertical axis turbines and horizontals was done in the early 1980s in the Altamont Pass. And the verticals killed about half the number of birds as the horizontals. And those are two-bladed flow wind turbines. And a three-bladed turbine is going to be different than a two-bladed turbine. So there is evidence already that verticals do not harm birds like horizontals do. But what we're going to be adding is technology, either DT Bird's motion detection technology, which it's out of Spain, and they've been developing in Europe for, decades. And it is able to see pixel changes, and the algorithm can tell you what bird it is based on the pattern of the pixel changes. And if you know if the program says a bird is coming towards your turbines that is known to not be able to see and avoid your turbines, it triggers a deterrence event. And if you know that bird is not going to be deterred, it slows down your turbines. So instead of at 50 or 60 miles per hour, it's down to 5 or 10 miles an hour until the birds pass. Then the cameras say, oh, birds passed, start it up again. And you have a big field of your turbines. You're not shutting down every turbine in the field. You're shutting down the turbines in the field where the birds are coming to. Out of Greece, there is a company called Envisionist that has super high technology imaging software, and it takes the actual image of the turbine, the blade, the bird from 300 meters away, and then can send a deterrence or turn off the tall turbines or our turbines before the bird gets there. And these run 24/7, so you can see owls and bats at night. So every one of our projects is going to have this technology on them, so we can more rapidly collect the data to say, up, we need to shut our turbines down. These kinds of birds are coming in. Or nope, no problem there. Those birds always see and avoid our turbines.
Well, thank you for all that. That's very interesting.
All right, I see Nat Martin, you've got your hand up.
Hello. Thank you. This is a great conversation. I had a question regarding wind speed in terms of when I know before, and let me back up. When I first got out of college, I worked for a company called U.S. Wind Power, Kinetech.
Kinetech.
And they went down when deregulation came in. But I remember that those turbines at the time, they were variable blade, and they wouldn't start until, I think, I'm trying to remember, 5 or 10 miles an hour wind, and then they would shut off at around 40 or 50. What are the limits on these?
We're going to start around 10 miles an hour.
Okay.
And we'll shut off around 60.
And is that the same range for the new horizontal, or are they
some
different?
of those horizontals can start at 6, 7 miles per hour. Most of them have to shut off pretty, because, somewhere around 50, 60 miles an hour. But remember that energy is so low in the low wind speeds that it's really very little energy is being produced by any turbine operating in less than 10 mile per hour winds. So you then have to measure, well, am I using up my, turbine for very little energy output? So there's a lot that goes into that, but it's bragging rights, a lot of it, because the public doesn't know that there's so little energy in the low wind speeds.
Right. Well, thank you very much.
Good.
All right. I don't see any other questions in the chat. So, and I believe we've got the
Sorry, one question here.
Yeah, go ahead. Yeah, Osama, go ahead.
So this is more on the functionality of the turbine. So when the wind's going in a certain direction, it looks like one of the blades is going to be pushed to rotate, but then the other blade is going to be coming back around against the wind. So how does that impact kind of the efficiency in the output of the turbine?
That's an excellent question. So vertical axis turbines were kind of dropped in the late 1980s because the horizontal axis turbines started getting bigger and bigger, and they realized that the efficiency of the horizontals, because they could yaw into the wind, was going to always be more efficient than a vertical axis turbine, which rotated back into the wind. And as it rotates back into the wind, there's going to be drag on that blade. So they're predicting that the CP max, the maximum efficiency of verticals, was going to be somewhere around 40%, 41%. And horizontals were going to hit close to 50%. The Betz limit is 59%. So you're really not going to get much more than 50% output from any kind of a turbine. But that's a significant difference between 40 and 50. And it was one of the reasons why the work on verticals was dropped. They could never imagine them being as efficient as the horizontals. But the breakthrough was the coupled vortex effect. When you place these turbines close together, and it causes the wind to speed up into the gap and spills wind to each neighboring turbine, well, that overcomes the increased drag that the vertical axis turbine has when it returns back into the wind. So that is where you will get your increased efficiency to overcome the drag problem.
Okay, that makes a lot of sense, and great presentation.
So we'll open it up to anybody else who has questions. Feel free to unmute yourself and ask your question. I don't see any other hands that are up or any other comments in the chat. Hearing nothing, I will say thank you everybody for your attention today. It's been an excellent presentation. I learned way more about wind power than I ever had known before. It sounds like a very cool field to be in, and I know as we Californians are always looking for what's our next best energy source beyond something that's coming from the ground. I think this has hopefully a lot of potential for future adaptation and adoption here in the state of California and potentially all over the world. Now, Sean, if you want to go ahead and stop the recording.